Hello everyone and welcome. In the previous episodes, we looked at Kubernetes pod networking in great details. Specifically, in part one of those series, we looked at container networking. As you know, containers are the building blocks of Kubernetes pods. In episode two, we looked at pod networking in Kubernetes. We looked at CNI, which stands for Container Network Interface. We also looked at Flannel CNI plugin. In episode 3, we looked at Calico CNI, which is a very popular CNI provider for Kubernetes users. And I provided a really great depth information. In this episode, we will look at Kubernetes services. Specifically, we will cover Kubernetes Control Plane and walk through how pods are created. This is kind of give you an overview of what the control plane is in Kubernetes. You might have heard about them, but you may not know what they are and how they're actually tied into pods and networks. We'll cover that. We also learn what a Kubernetes service is before jumping into and doing anything, basically understanding what the service in Kubernetes actually means. We also will look at Kube-Proxy and CoreDNS. So these are kind of fundamental components of services in Kubernetes. We will look at different types of services, such as ClusterIP, NodePort, LoadBalancer, and Headless services. We will also look at how service discovery is done in Kubernetes. What you are seeing is a simple Kubernetes cluster consisting of Kubernetes master and a single worker node. And we go through these components and explain what each one does. On the Kubernetes master, we'll have the control plane, which consists of etcd, which is a database, and all the objects that are created and their states are recorded inside etcd. The API server, which is the interface to the whole control plane and specifically to the etcd. So all the communication to and from etcd will need to go through the API server. We have control manager, which hosts many Kubernetes controllers, and each controller is really what's known as a control loop. In robotics and in systems, a control loop is a non-terminating loop that regulates a system. For example, a thermostat is an example of a control loop. When you set the temperature, you set the desired state. And it's the job of a thermostat to ensure that your temperature remains at your desired temperature. And these controllers do exactly the same thing. They manage objects and they make sure that those objects are at their desired state. Then there is scheduler, that when you create pods, ensures that the pods are assigned to nodes and they are hosted inside nodes. So it looks at the nodes and see which one has the capacity to host newly created pods. On the worker nodes, there's kubelet. Its job is to initiate creating containers and to ensure that containers are healthy. There's also CRI, which stands for Container Runtime Interface, and it's basically an interface to the container runtime. Examples of container runtimes are Containerd and CIRO. So those are CRI compatible. So going forward, all the container runtime needs to be CRI compliant, which means that although today, at this moment, Docker is supported, Docker runtime. Going forward, the next version of Docker and Docker runtime will not be supported as a container runtime. So right now, instead of the CRI, there's another component called Docker shim that interacts with kubelet. But going forward, Docker Runtime will not be there, so you will need to install either a containerd or CIRO to be compliant. And CNI plugin, that is primarily job is to make sure that pods have networks, so that all the networking such as namespaces and Ethernet interfaces and so on. And Kube-Proxy will dive into that deeply a little bit, but its job is to manage the services that run on a node. We also have host network namespace and everything related to the networking, such as the IP addresses, the Ethernet interfaces, the firewall rules, they all live inside the network namespace. So let's see what happens when we deploy an application into Kubernetes. Let's say we go to the command line, we issue kubectl, create deployment, and our deployment name, I call it hello world, and then we specify where the image is coming from. That's a path to the library that contains that container. Then the first thing that it does when we hit enter, kubectl creates a manifest and then sends that manifest through API server to etcd, and then that deployment is persisted. And then immediately it returns hello world created. Obviously at this point the application is not created, but it's kind of telling us that we received your order and we are working on it to make that happen. Kind of like when you go to a restaurant, you talk to the waiter, it happens to be API server in this case, and makes your request for your food, and the waiter takes your order to the kitchen and then submit it to the chef, comes back to you and say, yeah, I put your order. And then what happens next is the controller, which is responsible for deployment, connects to etcd and asks, do I have anything for deployment? And say, oh, yes. And then updates the etcd and says the replica set to 1. In this case, you might wonder, where did it get number 1 here? When we issue this command from command line, it implies the number of replicas. That is the number of required or desired pod is 1. So that sets to 1 and then goes back to sleep. So, and again, at some point, another controller, in this case, replica set controller comes to life, goes, checks the replica set and says, oh, you need to create one. So that update that to pod pending. And then at some point, scheduler wakes up, checks to see what's anything worked for him, and says, oh yeah, I have one pod, and then it updates the status to, assigns that pod to a node 1. In this case, we only have one node, so that kind of by default, it assigns it to that node. And then at some point, kubectl connects to API server, checks etcd and sees something for it, and say, oh yeah, there is a pod assigned to me. And then it updates the status to pod pending. And then it calls CRI, or Container Runtime Interface, which in turn talks to Container Runtime. Container Runtime then checks at the request and then checks its library to see if this image is already in there or not. If not, then it downloads that and eventually runs the container. So at this point, we have a pod which doesn't have any networking yet, and that's the next step. kubectl to CRI talks to CNI plugin or Container Network Interface, which the first thing it does, it creates the network namespace. Then it creates the virtual Ethernet pairs. One is created on the pod, the other one is installed on the host. And now we have a pipeline. This is a pipeline that both the host and the pod are used to communicate with each other. Then it assigns an IP address to this pod. Now the pod has an IP address. Next thing it does, it sets the default route for the pod. And then finally, it updates the host and set a route how to get to this pod here. So now we have a complete set of, or the communication between these two is set up now, and the pod is able to talk to the host, and then also through host, you can communicate to other places. And the last thing that kubelet does is, again, updates the etcd database through API server, and sets the update to pod created. Now at this point, we have reached our desired state. We have one pod which has set up. It's all networked and ready to go. And from this point on, the whole system is watching this pod and making sure, like the thermostat ensures that we have one pod at least running at all time. Even if we delete the pod manually, it will be recreated for us. If the node goes down and comes back again, it recreates the pod. So this now, we have achieved the desired state. This is my setup that we'll be using for the demo part. So I have a cluster setup. I have 3 nodes. One of them is master and 2 worker nodes. If you don't have a cluster setup and you want to follow along, you can go ahead. I have a couple of videos that walk you through setting up a scale-out Kubernetes cluster, one on Ubuntu and the other one on CentOS. So if you want to do that, go ahead and do that, and then continue from there. We already talked about these components and what they do. The only thing that you might be see new is this tunnel 0 on both of these. I'm using Calico out of the box. I'm using the default Calico setup, which uses IP and IP. And then it sets up 2 interfaces. That is, on each node, it set up an interface. It's called tunnel 0, and all the communication going across from one node to another, it goes through tunnel 0 and then through the default interface of the server and goes across to the other one. So next we are going to the command line, actually practice what we talked about in the last slide. So we are in Visual Studio Code now, and we are going to deploy the same application that I showed you during the presentation part of the video. And the command is kubectl create deployment. Deployment name is hello world. And again, the image we're getting from Google. So we have 2 options, either run that from command line, or we can create a YAML file and then execute the YAML file. This is the preferred way of doing this, but it's easier when you're doing demo, just run that from command line. But this is a kind of proper way. So let's go through that quickly. We have the API version, that's version 1. The kind, we need to specify that as deployment. And the metadata, we have name, that's the name of our deployment. And there's specs, we are specifying the replicas as one important one, how many replicas you want. If you don't specify, it takes that one by default. The match labels, this is what are the pods that are included in this deployment. So this kind of loosely coupled scenarios where we match what is included in this deployment by having the labels, that is the containers will have this, need to have the same label. So it's looking for any container that has hello world, its name. So, and the template, that is a template for the pod. So we have the labels again, and this is the label. So this, we need to match this. Basically all this labels or this container, they have this label, and then that label will be matched against our deployment. And then further down, And the containers, again, we name it Hello World. And the image that we are getting it from, again, we're getting it from Google Library. And the container port, what port is running on. So this is exactly as this. So let's go ahead and run that. And you can see Hello World was created. And then to kind of double check that on line 101, kubectl get deployments. So let's go ahead and run that. And this is our Hello World application we just deployed. On line 104, kubectl get pods. Basically, we just want to make sure that we see that the pods were created and what the status is. And as you can see, Hello World. We have a single pod that starts with Hello World. And this is the IP address, and that is where it was created. Okay, so far so good. Now on line 107, we want to scale up our deployment. So we only have one pod at this point. On line 107, kubectl scale, replica is equal to 4, and the deployment name, Hello World. So let's go ahead and run that. And as you can see, it says was scaled. And on line 110, again, we're going to verify that. kubectl get pods minus O wide. So minus O wide gives you more information, such as the IP address of the deposit that was created. So now, as you can see, now we have 4 pods. So that it has reached the desired state of having 4 pods. I'm going to grab one of the IPs, like this guy here, and on line 113, we are going to test the application. We're just going to test the application that we just deployed directly. So I'm going to call one of the pods directly. So curl HTTP, the IP address of the pod, and the port, if you recall, is 8080. So let's go ahead and run that. And as you can see, this is the results that coming from the application itself. So it's Hello World, the version and the host name that is running on. So we have now our deployment completed. Next, we'll see kind of visually how our test environment looks like. This is the view of our cluster now after deploying the new pods. I've removed some of the components such as kubectl and CNI and CRI, etc., to make room for pods, to showing the pods better. So we have now 4 Hello World pods, 2 on each node. So we have node 1 and node 2. I also created this test application, test pod, that I'll be using in the following demos to call the service from the services from there. But just ignore that for now. So as we saw in the demo part of the video we just completed, we'll be able to now to access the application by calling the pod directly, that is by curling into the pod using the IP addresses. But there are a couple of big problems with this approach. First, pods are ephemeral. Ephemeral means that they come and go. They don't have a permanent life. They could be deleted, could be, nodes could go down and come back again, and those pods are created. So those IP addresses will change constantly. So we can't really depend on the IP address of the pod. The other problem is not load balance. So we have to know each one of those pods, and either in our application, create our own, goofy load balancer that every time, call a different pod. So this is not going to work. So in the real world, you will need a load balancer, and you need a virtual IP address where you can call that rather than calling the IP addresses and the pods directly. And that is the kind of the meat of our discussion in this video. How do we do that? And services is the way that in Kubernetes we create the load balancer and also provide a redirection or creating a virtual name or IP address that we can call from anywhere in the cluster. So let's see what services are and how they work. A service is really an abstract way to expose an application running on a set of pods as a network service. The keyword here is a network service, which provides abstraction on a subset of pods. It provides persistent endpoint for the clients through virtual IP. So the client will have to know only one thing, and that is a virtual IP. They don't know, and they don't really care how many pods are behind that service. They don't really know or care about what the IP addresses are. Next point, relate to the first point. As we mentioned, pods are ephemeral, which means that they may be deleted, recreated, and clients really shouldn't be binding directly to those pods, and service provides that abstraction. It load balances the backend pods, which is very important service. It automatically updated during pod controller operations, which means that when you add, for instance, you increase the number of pods behind a service or decrease the number of pods, then the services controller detects that and adjusts the endpoints representing those pods accordingly. There are several different types of services, such as ClusterIP, NodePort, and LoadBalancer. Now let's see how services work, kind of an overview. Services match pods using labels and selector. So when you create a deployment, in that deployment there is a pod section, and then for that, in that section you specify what is the label for those pods. And when you create a service, you tell the service in the selector section that these are the pods that I'm looking for, and those pods are represented by this label. And that's how pods and services are matched. It also creates and registers endpoints. So endpoint is actually a different object, but when you create a service, it also creates endpoints for those pods. And endpoints is really basically is the pod IP and port pair, which represent this service. Kube-Proxy, which is installed on each node, it creates the virtual IP address and also programs the Iptables to provide L4 load balancing. So in this demo, we're going to use Iptables, but there's also in different modes, there's IPVS mode. That is, rather than using Iptables, we can use also IPVS, which is a newer method of doing that. There's also the older way of doing that was in user mode, but that's very old, is not being used anymore. So for this demo, we're going to use Iptables. I'll explain how that works in Iptables. So in this section, we are going to talk about ClusterIP service, but before getting into that, I just want to go over our infrastructure again. So I have a master and I have a couple of nodes, node 1 and node 2. And we have a number of pods on this side and a number of pods on this side. So Hello World service is installed on these two pods over here and these two pods over here. I'll be using this test pod to call a service that may either answered by one of these pods over here or over here. And I'm using Calico CNI, or Container Network Interface. Basically, CNI provides networking for the pods, so they will be able to talk to each other and also talk to pods on the other side on the other server. When we install CNI out of the box with IP and IP, which I'll be explaining a little bit later, that installs a router over here and a router over here. So the communication, let's say this guy wants to call a service on this side, the communication will need to go to this, it's called tunnel, basically is a router. And then that router needs to talk to the other router over here, and then that router delivers the message or call the service on this side. So that's basically the basic setup of CNI when you install Calico, IP, and IP. So what does IP and IP means? So there could be situations where these routers cannot talk to each other directly. For instance, these two, the nodes are on different subnets, and then maybe there are many hubs between them. So it's very difficult to create direct communication between these two. And we don't want to change the underlying network, which is the node network, in order to accommodate the communication between these the pods on different servers. So that's why the container, the CNI providers such as Calico or Flannel, they provide what's called an overlay network. So they set up a network on top of the existing underlying network without making any changes to existing network. And that makes the communication possible. In case of Calico, by default uses IP, and that's what I'm using here. When the request is on its way to destined for a service on this side, that packet, that IP packet, is put inside other IP packet, and that IP packet is sent from this server to this server. Because this server knows how to communicate with that server, no matter how many hubs are between them. So that packet is put inside the bigger packet, and then when that packet is delivered here on this side, the inner packet, which contains a request from this pod, is retrieved and then is handed over to this router here, and then router knows how to deliver it to this pod. So again, it happens behind the scene. This this underlying network doesn't know anything about that. It's happening kind of hidden from it. But it doesn't really matter because that accomplishes what we need to do. Let me give you maybe an example to make it a little bit more clear. Let's say these pods are people living on this side. This is a city, and this is a different city. And we have some people living on this side and some people living over here. Let's say this person wants to send a piece of mail to this person over here. He or she puts that piece of mail in his mailbox or her mailbox, and the mail carrier will bring it over to the post office. So this router really can think of it as a post office. And then this post office will need to send that mail to the other post office on this side, and that post office knows how to deliver to this person over here. Ordinarily, there's no problem, but there might be a situation where, let's say there's a body of water, let's say there's a lake between these two post offices. And so the truck cannot really travel over the water, and we don't want to spend the infrastructure to set up a bridge between these two post offices. However, we do know that there are regular flights from this airport to this airport. So what we could do is the post office will say, okay, we'll put the original piece of mail in another envelope, which is specific to the airline, and then hand it over to the airline. Airline would deliver it over here, and somebody from post office, let's say in this airport, retrieves the original piece of mail and then send it to this post office here, and then that post office knows how to deliver it to this person over here. So this is kind of a high-level view of how IP and IP works. Again, I'm using Calico by default, which uses IP and IP. So it kind of gives you a little bit of understanding when we go through this, not to get kind of confused. So now let's concentrate on ClusterIP. So we can create a ClusterIP either through command line, like here, or we can do it through YAML. And I'll show you the YAML instructions when we get to the demo part. So we can say kubectl expose deployment, and the name of the deployment that we want to expose, that is, we want to create a service for. In our case, is our simple hello world. -- port, that is what port number this new service will be listening on. We say 8080. And -- target port, that is the port number that the service actually is listening on the pod. This could be the same, or we could pick a different port here, and then Kubernetes automatically forwards the request to this port over here. And -- type is what service type you're creating. In this case, we say ClusterIP. If you don't specify the type, it by default creates a cluster IP. So if you're just creating cluster IP, we can omit this part. So when we hit enter, again, request goes to API server, it gets validated, and then it's persisted to HCT. And then at some point, a service, this controller wakes up, examines the service request, and creates an endpoint object. An endpoint is basically what pods are involved in the service, and this is the list of IPs of the pod. So we have 2 over here and 2 over here. And then this proxy here at some point wakes up and then does 2 things. It looks at the request here, creates an IP address, a virtual IP, and also programs the IP tables. That is a NAT table inside IP tables, and then creates a rule. The rule is simple. It says any traffic that is destined for this IP and port number, intercept that, and then rewrite the IP, the destination IP from this to one of these endpoints that it selects at random. So in effect, it creates a load balancer here. So let's say this pod here wants to consume our service. So it says issues curl HTTP, the IP address, the IP address of the virtual IP, and the port number, which is here. And when it does that, it creates a request, basically. Obviously, that request is an Ethernet frame. Inside that would be an IP packet. So I'm just going to summarize that. We are only interested in, for this discussion, in the source and the destination. So the source would be itself, the IP address of itself, which is this one. And the destination is the cluster IP. So the request then goes out, is intercepted here, and then one of these endpoints by random is selected. And also on its way out, the destination changes from the cluster IP to a specific pod, which is this pod. So now the request will be sent to this pod. And on its way out, this packet, the original packet, is put inside an exterior or other packet, and that packet is then sent to the server, which is again over here. The original packet is retrieved and is handed over to this router, and that router hands it over to this pod, executes that, and then it creates a response. And the response basically says, hello world, the version number, and the name of the pod that answered. So that's our simple response. So the response will be sent on its way out. So the source again would be the source of this IP, of this pod. The destination would be the destination of that pod. So again, it goes out. Before leaving the server, over here, again, an exterior or other packet is created. This response is put inside that and is sent to the server here. Again, over here, this response is retrieved from the other packet, and then it sends back. And then over here, it does as SNAT or source NAT. Because remember, we changed the destination coming out of here from the IP address, from the cluster IP to this pod here. And on way, going back now is reverse. The source now changes from this to this IP address, because that's what's the pod is expecting, because the pod is expecting to get a response from a service with this IP address. So that's why, again, the source is changed from the IP address over here to the cluster IP. So it sends to this, and then the pod gets a response. So that's this is kind of end-to-end traffic of how the cluster IP works. Obviously, the number of hops here that you saw, and I kind of even simplified. There's more is involved in that. I kind of simplify that to make it a little bit more easier to understand. So at this point now we have the response and everybody's happy. So as long as all the services that are consuming the service are inside the cluster, then we are done. We don't have to do anything else. However, the real world is actually obviously more complicated. So obviously there might be situations, and that is almost always the case, that there are clients outside the cluster that want to consume the service. So how do we expose that? And one way of doing that is through NodePort, and that is something that we will discuss next. Before moving on, I want to talk about something very important here. When we use ClusterIP or other services that we'll be talking about shortly that depend on ClusterIP, and if one of the pods that is selected as part of his load balancing and that pod is not responding, it will not try other pods, which means that the application actually dies. So it's very important to add a liveness probe to your pods if you're using a ClusterIP. In that, when we do that, then Kubernetes will not consider that dead, kind of take that dead pod out of the equation. And so when the request comes here, Kubernetes will not see the ClusterIP, and load balancing will not see that dead pod, and everything works. So just keep in mind, make sure you add liveness probe to your Kubernetes pods when you're deploying them. The other note is using ClusterIP really implies that all the clients are inside our cluster. If your clusters are all inside the cluster, then you're done. However, it almost in all situations, there will be clients that outside the cluster that will be needing to consume the service. And there are other services that we can use to get around this issue. And we'll be talking about those next. Now let's take a look at the NodePort service. So the NodePort service, all really it does is exposes the ClusterIP, virtual IP to the outside world. And let's see how it does it. First of all, to create a NodePort service, the syntax is exactly the same as ClusterIP. The only difference is for the type we specify NodePort. So when we execute that, again, it does the same thing as it did before for ClusterIP. It will create or it will program the IP tables, adds the rules for load balancing. It creates a ClusterIP, and it does it in all servers. But the only thing that it does additionally is it creates picks a random port. And this is configurable. You can select whatever port that you want. And that exposes those servers, so it opens a rule or a port on every node participating in the cluster. So the client now can connect to this service, to this cluster virtual cluster IP through the IP address of the server and this port number that was chosen for it. So let's take a look. Let's say we have a client is external to this, is not part of our cluster. Kubernetes is a cluster. And let's say it wants to consume our service. So the way it does it is it needs to connect to, uses the IP address of the server and uses the port number of the node port, not the cluster IP, because it won't be able to reach inside. And then it sends a packet or request out. Again, this is a simplified version of the request. We got the source IP, which is the IP address of this client. The destination is the IP address of the server. It can pick any server. For this example, let's say it picks this server. And the port number of the cluster IP. So when it does that, the request comes in. And over here, it does both, it does natting for both for the source and destination. So it changes the source ID, IP from that server to the server here. And the reason for this is, let's say this request goes through and then one of these pods responds, and then if it doesn't change the source ID, the request, when the results come back to this server, it will see the IP address of this as the responding server rather than this. And because this service is still in session and expecting to hear from 10.00135, but instead it will hear from 10.00164. So then it rejects that. So to get around that, it does an adding both for server, for the source, and for destination. Well, destination, obviously, it needs to change it to this cluster IP, so it's changed that to cluster IP and the port number. So it goes again through the same process. It picks one server at random, one pod at random, and again it does the DNAT, so it changes the destination IP address from the cluster IP to whatever pod that it's chosen, and it goes through the same process. And then eventually the server, the application runs again, we get the same result, hello world, and so on. And then it again goes, sends a request back to the other server. It's like exactly as before, nothing really changed. The only difference here is now, because this came from the outside client, we need to again change the source back to 10.00135, which is this server, and the destination to IP address of this client. So when you execute again, comes back here, and we'll see get the result back. So the process is really the same, and the only difference is the client came from outside the cluster. So that's what the NodePort does. It exposes the cluster IP to the outside world. Now you'll see a problem here. You'll see that, again, this client needs to make a decision which server to connect to. And that's not good, because if this server is pointing to this server and this server goes down, then what happens? The application crashes. So we need a load balancer here. And that's what we're going to talk. So the NodePort really service is really meant mostly for load balancers to load balance the nodes of the cluster, so client can connect to a virtual IP like a cluster IP, but from outside. So they need to go through some sort of load balancing. If you host your cluster on a public cloud provider such as Microsoft, Google, or Amazon, then you can take advantage of a service called Load Balancer service, which automatically, when you create the service, it creates a load balancer and shares the load across all the servers in the cluster. The command for that is exactly the same as before. That is, to specify the name of the deployment, the port that the service is listening on, the port number of the application that is listening inside the pod, and instead we just say load balancer as the type. So once we execute, as usual, it creates a cluster IP node port, it programs IP tables, and then it waits for a provisioning to complete. And once it's completed, and then it adds a public IP and port number through the load balancer where the client can connect. So if you have a client that wants now to consume this service, again, now they will use the public IP address and port number of this load balancer. And every time that hit the load balancer, it selects a different node. So it says simulate that. So this time, and then next time, this server is selected. So if we are on-prem situation, this is not going to work. So we have to actually manually create our own load balancer. Now let's take a look at some special, what I call special service types. Those are not your normal services, and they have their use cases. So before jumping into those, let's summarize what I call normal services. In that scenario, as we saw, we create a deployment, and then in that we specify what pods are included, and those pods are labeled. For instance, in this case, we say app hello world, and then we have a selector in the pod, in the deployment manifest, that ties to those pods. So that kind of that to emphasize. So this will match. So these pods will be part of this deployment. Then we define a service, as we've seen so far, and in that we normally specify what type of service this is. For instance, ClusterIP or NodePort. And then we have a selector section that matches the pods that we already defined or deployed to this service. So in effect, this service now has a selector that is, it only binds to a specific type of pods and also provide load balancing. Now let's take a look at the first type of what I call special service types, and that is services without selectors. So as we just saw, we use normal services to provide abstraction over a number of pods, but we can also abstract other kinds of backends. For instance, if you're using, for instance, a database during the development and you have a different for production and you want to separate those out, or you want to point your service to a service in a different namespace or another cluster, or you have, you're gradually migrating your workload, backend workload to Kubernetes. So you want you want to reuse your current services until you're ready to move all of them to Kubernetes. And you kind of want to leverage those. And we treat it kind of like Kubernetes objects. So let's take a look at how we define a service without selector. So as the name suggests, we define the service as usual, we name it, we provide ports and target port and so on. But as you can see, there is no selector. And because the service has no selector, it doesn't create an endpoint. So we can create an endpoint manually, and then we can then provide redirection to where we want the service to come from. So this is how we create an endpoint. So the kind is endpoints. We name it, and then over here is the important part. We have the subsets, and then we have addresses, so the IP address of the service that this service will provide. So this is a redirection to another service somewhere else, and the port number. Important note is it can be any service, but it cannot be a ClusterIP. So ClusterIP are not supported here. It could be regular services that you have somewhere else or in a different namespace. Another type of service is called external service. An external service is a special case of service that does not have selector and uses a DNS name instead. Service type external name maps a service to a DNS name, not a typical selector such as my service. This is how we define that. The kind, again, is service, obviously has a name. And this is an important part here under spec. We specify the type as external name. And then this is a fully qualified DNS name. So this is very much similar to services without selector. Again, really a special case of that. Where instead of the IP address, we have a fully qualified DNS name. The last category of services that we looked at today are called headless services. And sometimes we don't need load balancing, maybe we don't need a single IP, but we do need to interact with individual pods. In those cases, we can create what is called as headless service by explicitly specifying none for the ClusterIP. When we create a headless service, a ClusterIP is not allocated, and Kube-Proxy does not handle these services. and there's no load balancing or proxying done by the platform. And do note, however, that although we don't get load balancing through a Kube-Proxy, we still get load balancing through DNS, a round-robin mechanism. To define a headless service, we just use, again, the kind is service. The only difference is for ClusterIP, we specify none. When we create the service that way, if we, from a pod, inside any pod, if we do an NS lookup for the service we just created, then we'll see that we'll get, let's say in this it has 4 pods. We'll see that each one of those pods will have a DNS entry, and we can get their IP addresses this way. If we contrast that with a normal service, when we do that, all we get is a cluster IP for the whole thing. So this we don't get, so for headless services, we actually get a DNS name for each one of those pods. Now that we learned a little bit about services that Kubernetes offer, let's talk about Iptables, because I mentioned Iptables quite a few times when we were talking about the packets and routing. So Iptables is really, we can think of it as the Linux firewall system. This firewall system interacts with the packet filtering hooks in the Linux kernel's networking stack. These kernel hooks are known as a NetFilter framework. The Iptables firewall uses tables to organize its rules. These tables classify rules according to the type of decision they are used to make. For instance, if a rule deals with network address translation, it will put into the NAT table. If a rule is used to decide whether to allow the packet to continue to its destination, it will be added to the filter table. Within each Iptables table, rules are further organized within separate chains. While tables are defined by general aim of the rules they hold, the built-in chains represent the NetFilter hooks which trigger them. Basically, chains determine when rules will be evaluated. A rule is a statement that tells the system what to do with the packet. Rules can block one type of packet or forward another type of packet. The outcome where a packet is sent is called a target. A target is the decision of what to do with a packet. Typically, this is to accept it, drop it, or reject it. So this shows you various types of tables within Iptables. So those are filter, NAT, Mangle, and raw. There's also another table called security that, for brevity, I'm not going to talk about that today. And as you can see, each table is governed by various chains, and not all chains or the timing of the rules apply to all of the tables. So let's take a look at some of these chain and what they mean. The input in the rules in this chain, that is in the input chain, control the packets received by the server. So when the packets arrive. Output, this chain controls the packets for outbound traffic. So before the packets leave the server. Forward, this set of rules controls the packets that are routed through the server. Pre-routing, this chain assigns packets as soon as the server receives them. And post-routing, the rules in this chain allow making decisions to packets after they leave the output chain. Now let's take a look at each one of these tables very briefly. The filter table is used to make decisions about whether to let a packet continue to its intended destination or deny its request. It is known as filtering. This table provides the bulk of functionality that people think of when they discuss firewalls. Everyone thinks about what packets are allowed or not allowed. So that filter table is responsible for that. The NAT table, we talked about that before. The NAT table is used to implement network address translation. As packets enter the network, rules in this table will determine whether and how to modify the packet's source or destination address in order to impact the way the packets and they respond traffic are routed. So we looked at it in the previous slides when we talked about how packets are routed by the services. We also, and this is really the main concentration of our discussion for this demo and this video, is the NAT table. And we'll talk more about that during the upcoming demos. The manual table is used to alter the IP headers of the packets in their various ways. For instance, we can adjust TTL, or time to live, value of a packet, either lengthening or shortening the number of valid network hops the packet can sustain. Other IP headers can be altered in similar ways. And another important thing that it does here is this table can also place an internal kernel mark on the packet for further processing in other tables and by other network tools. This mark does not touch the actual packet, but it adds the mark to the kernel's representation of the packet. The last one, the raw table, the IP table firewall is stateful, meaning the packets are evaluated in regard to the relation to previous packets. And we saw that with the NAT table, for instance, when we were talking about services, and sometimes when we change for instance, the source IP of the packet, then the response comes back, then we kind of change it back to what it was. So firewall, most of these, especially when we set up a session between the client and server, the firewall keeps track of what's going on through what's called a contract system. But not all these packets are needed to be monitored. And the raw table is really used to exempt packets from connection transfer. So the connection, for the ones that we don't care about their status and when they arrive and how their relationship was with the other packets, this table is used to kind of keep track of those. So it's demo time. Let's do the demo of some of the stuff that we talked about. Before creating any services, let's kind of review what we did in the last demo. In the last demo, we created a deployment called Hello World with this image, and then we increased the number of pods from one, which this one, to 4. Now we have 4 pods supporting that deployment. So let's go ahead and take a look at our pods on line 129. kubectl get pods -OY, and this is what we see. So we see Hello World is deployed, and you can see what service, what nodes are running on, and their IP addresses. Next step is to actually create a service. So on line 133, kubectl apply -f, and this is the name of the YAML file. So let's go ahead and take a look at that YAML file. And it's pretty simple. Basically, you specify the API version, the kind, which is service, metadata, you specify the name and the label for this service, and their specs. You specify what type of service this is. I specify NodePort. If you don't specify anything, it will create a ClusterIP. Also a reminder, NodePort also creates a ClusterIP. And then under selector, what pods are included as part of the service, and any pod that has this label, app Hello World, so that will be included in this service. So this service will be load balancing and provide external, actually access to the services running inside those pods. And the ports. We have 8080, so that is for the port number of the service that is listening on. And the other one, TCP protocol, TCP, and the target port 8080. This means what port the service itself inside those pods are listening on. And the last one is NodePort, and the port number that we would like to use. If we don't specify anything, any port number here, it will automatically select a random port between 30,000 and 32,767. So we can say, hey, we want to specify the port number ourselves, so that is 30,001. So let's go ahead and run that. And as you can see, the service has been created. Scroll down a little bit. We can do achieve the same thing by running this command, kubectl expose deployment, and that's what we've been doing so far. So in this case, I did not use this command. Imperatively, I actually use a declarative inside YAML, which is preferred. Okay, let's go ahead and double check the service that we just created on line 138 and get some more information. So kubectl get services -oy. So let's go ahead and run that. And as you can see, now we have hello world service node port. The type is node port. This is the cluster IP. 8080, this is the port number that the service is listening on. And node port is 30,001. So you can access the application or service from outside by hitting any of our nodes and specifying the IP address of any of the nodes and this port number, and we'll see that in action shortly. Now, let's go ahead and SH into one of the pods on this one, on line 140. This is to simulate that we have a service that is running inside pod is calling the hello world service. We can also obviously hit it from the node itself, but let's go ahead and do that from inside the pod. So we are now inside the test pod, and then we can say curl HTTP and the cluster IP. So the cluster IP would be this. So let's go ahead and copy that and paste it here. So if we hit it now, if we on line 142 curl HTTP and the IP address of the cluster IP and the port, which is 8080. Let's go ahead and hit that. As you can see now, we'll get hello world, and it's coming from one of the hosts. If we hit it again, you'll see that it's coming from a different pod. So this is how the service is being load balanced. You can also hit the service if we don't want to use the IP address, and we will talk about that in the next session when we talk about DNS, but it also creates a DNS for the service, and the DNS name that it creates is actually the service name that we have, the hello world, NodePort, then dash. So this is the namespace of where we created it. By default, we are running in the default namespace, so that would be default.svc.cluster.local and the port number. So if we know the service name, then we can construct this DNS name, and that will be easier actually, rather than knowing the IP address. Now we can hit it with the DNS name. So let's go ahead and run that. And you can see now, you get the service and the results coming back. Okay, let's get and exit that. Now I'm going to execute this. I'm going to call the service from actually outside the cluster. And actually, I'm going to run it from Windows is a PowerShell. If I execute that, and we get the exact same thing, hello world, and this is the name of the pod. So this is a demo of the regular server or NodePort service, as we talked about earlier. Next, we are going to actually see how, we saw that here that the service is load balanced, and we talked about how the mechanism of how that is done previously and during the slides. Now we're going to actually see from the, we go to the shell, command shell, and look at Iptables and see how that load balance is actually accomplished. Let's go to command line, and this time you're going to run the commands from inside Linux terminal directly, not inside Visual Studio Code. That gives us more real estate so you can see it better. So the goal is to investigate how the load balancing of services that are hosted inside pods occur. And the command that we're going to use is Iptables -n means give us more information or verbose. -t means the table name, and the one that we are interested in is NAT. So inside Iptables, we are interested in the NAT table. -l means show us list of the list. And if we don't specify a chain name, so this is the chain name, it shows us all the chains inside Iptables, that many of them. But Kubernetes itself uses this kube dash services, so all the chains related to Kubernetes are inside that kube service. So when we run it, we'll see all the services that have been created by Kubernetes itself. So some of them are such as DNS, and the one that we are interested in is the last one. So this hello world NodePort. So this, again, within the that chain, now we have subchain, and this chain have their own rules. So these are the rules within this chain, and then these are actually subchains that have their own rules. So let's say, what is this rule? So this is the chain name. Basically, what it does is it says any protocol TCP, any source, but if the destination is this, which is the IP address of our cluster IP, then execute these subchain. So basically, when the request comes into Iptables, if it's destined for this cluster IP with this IP, then execute. Then go to the next one chain. So let's go ahead and let's look inside this chain. And you will see that there are 4 rules, and each one corresponds to a pod. So this is how this is where the load balancing actually occurs. So when we hit that IP address and it comes inside this, and then one of these is selected. So let's look at the criteria. The first one says the probability is 25%. So we have 4 pods. The odds of hitting the first one is 25% or 0.25, right? If the first one is not selected, it goes to the second one. The odds becomes 0.33 or 1 in 3, right? If that's not selected, it goes to this one. The odds is 50% because there are only 2 of them left. If this is not selected, then by default, it goes to the last one. So this is how the load balancing of pods occurs. So let's go ahead and peek inside one of those. So again, we can go one level deeper and see what's inside this. Let's look at this one first, DNAT. So basically, the DNAT operation happens here. What are the criteria? And it should be TCP. And the source could be anything, the destination. So basically what it means is, if we get to this point here, because it still has the IP address of the service, it says do a DNAT, destination NAT, and change the destination from the IP address of the cluster IP, which is this, to a specific now IP address of the pod and the port number. So we're going from 10.96.20.36:8080, that is the port number of the service that is listening on here. It then changes that to 192.168.233.199.8080. So basically we change the IP address and the port from the cluster IP to the service that is listening on this pod. And the first one, Kube mask, and this is the source IP. Basically, as you can see, this is the same IP address as this one. If by chance, if it happens, for instance, if the service for some reason calls itself, or maybe another service inside that pod that calls the service, the hello world service, and it happens to route it back to itself, then by default, if we don't do anything about it, the service kind of responds locally and bypasses the whole Kubernetes service. So what happens with this Kube mask? Basically, the source is changing from the IP address of the pod to the IP address of the node which is hosting it. And then it goes back. When it goes back, then it kind of continues the same route that it came, and then it won't circumvent the call. That's what it means. So hopefully that shows you a little bit of how the load balancing inside services work. The last topic that we will cover in this video is service discovery. Kubernetes clusters automatically configure an internal DNS service. It's called CoreDNS, which is really a very lightweight DNS to provide service discovery. And even as services and pods are created and deleted, Kubernetes keep track of those and then updates the DNS accordingly. So the CoreDNS deployment is exposed as a Kubernetes service. It's called KubeDNS. It has an static IP address and provides these services. First, the KubeDNS listens for service and endpoint events and creates DNS as services are created. So again, it's a service that watches as the services are created or deleted and accordingly adds or removes DNS records for those services. It assigns a service. Each service gets either a or quad A, depending if we are using IPv4 or IPv6. And the format of the service, as we talked about a little bit earlier in that previous demo, is the service name .namespace.svc.cluster. For instance, hello world.default.svc.cluster.local. Also on each pod, it sets the resolve.conf file, which provides the name resolution for that pod. And it sets it to the ClusterIP address of the KubeDNS, so that would be the resolver. So in this demo, we will see name resolution in action. So the first thing that we want to do is look at the CoreDNS. So the CoreDNS is actually implemented as pods. And on line 206, kubectl get pods, -n means namespace, kube system. So those pods are in kube systems. And I'm graphing to just display the CoreDNS. So let's go ahead and run that. And as you can see, in each cluster, it creates 2 pods, and those pods contain the logic for the DNS. So this DNS system is actually in these 2 pods. On line 209, we want to look at the service, the DNS service, and it is again in the namespace kube system. So kubectl gets services -n, which is namespace, and kubectl system. So let's go ahead and run that. As you can see, this is kube DNS, and this is the IP address of the cluster IP address of the service. Now we can use this IP to do some name resolution from the node. So on line 212, NSLOOKUP, hello world -no selector. So that was one of our services that we created earlier. And this is the full DNS name. And then this is the IP address so that is our resolver for this query. So let's go ahead and run that. So this is the result that we see. So we can get the IP address, for instance, of the service. Knowing the name, we can get the IP address, or the reverse. If you have the IP address, we can get the name of the service. Now let's look at a different namespace. I created another namespace called test. So on line 215, let's go ahead and look at the services that we have in that namespace. And I have one service called HR, and that is the ClusterIP address for the service. Let's scroll down a little bit. And then on line 218, and let's look up, so I'm looking, this time I'm going by the IP address and using again the DNS IP address. So let's go ahead and run that. And you'll see that this is the name, the record name. So this is actually the name of the service. The fully qualified name is hr.test.svc.cluster.local, because this is in a different namespace, so it's not default, so it's hr.test rather than hr.default, because now it's a different namespace. On line 220, let's go ahead and let me just clear here. Let's go ahead and SSH into one of the pods. And this is the one that we looked at yesterday. So we're going to call Hello World service, a NodePort from this service. As we saw yesterday, we can specify the fully qualified name. And if we run this, obviously we get the result. The results come back. Now let's look at the resolver and see what's in it. If you recall, we just mentioned that the CoreDNS updates the resolve.conf file on each pod to set the DNS settings. And as you can see, this is the result. First of all, the name server is, so that is the name server that this pod is going to use, the same one that we use up here for all name resolution. We can also see now it has this search. So this is the fully qualified name that is tagged to the service name. If we don't specify that, we can specify just, we can omit the svc.cluster.local. Again, it will be resolved, or we can even make that shorter and just specify the service name, and it will discover the full DNS name. And the last one here is, if we can't resolve, then that is this is what it inherits the search from the pod. So I'm using Comcast as my provider, and that uses, if you can't resolve any of this, then it uses, tries to resolve it going outside the cluster. So knowing that information, now we can say, so first of all, we saw that we can call the service as a fully qualified name. Over here, I'm just omitting the .local, so if you run that, again, we get the same result as before. We can even make it shorter and omit the SVC and the last part, the cluster. So if you run that, again, we still get the result. You can even shorter and just specify the service name, and that's. So this is, as you can see now, because we are in the same namespace, so we don't have to specify the name of the namespace. So this provides a very good way for us. So we don't need to know really deal with the IP addresses. If we know the service name, then we can construct the URL and consume the services that way. This concludes my video on services, Kubernetes services. I hope you'll find it useful. If that's the case, please give it a like, share it, and consider subscribing. This is a list of my other videos. I'll provide a link in the descriptions also in case you're interested to watch. Again, thank you very much and hope to see you soon.